In a world where light is not always what it seems. That hurts. Jeez, how those guys do it. Anyway, yeah. Alright, let's try to finish this up in this video. Infrared. First off, well, here's a picture of the sun in infrared, and again, you see different details. But you might be thinking that these different parts of the electromagnetic spectrum that aren't visible have different colors, like maybe microwaves are blue, uh, you know, infrared is orangey, ultraviolet is whatever that is, every color, X-rays are orange. But guess what? They don't have any color because our eyes can't see them, and color is only registered in our eyes in the visible part. So what we do is, it's kind of like art. We say, well, this is an infrared picture, and I'm going to assign a certain color to the bright parts of the the picture, and another different color to the dim parts of the picture. And that's where we're going to go from there. So someone who made this picture said, I feel like orange today. I think today's an orange day. So I'm going to represent this infrared picture of the sun in orange. And why not make the less bright parts black? And then kind of like scale from there. So as you get brighter and brighter, you get more and more orange, almost even sort of like yellow here. I guess I can't really see what that is. So anyway, it's all artistic in a sense. There is no real color because these are invisible to our eyes. Anyway, long story short. So this is the sun in infrared, and you can see other details that you might not have seen in other wavelengths, like this thing here. And let's watch a few videos of things in infrared. It's pretty cool. This first one is, they actually show you an infrared camera and what one looks like, and then they show you a bunch of other things, including a refrigerator, and how a cool refrigerator doesn't give off a lot of infrared light. So let's check it out.
Now it's time to look at an everyday object using an infrared camera. Hot things give off lots of infrared, while cold things give off less. And this camera can actually do what our eyes can't. It can see the variations in temperature. There are about 30 million fridges in the UK alone. What will the infrared camera reveal about this one?
You ready, Rich?
I'm ready.
So what you see?
Black and very dark blue. Most of the fridge is at +4 degrees Celsius, but because heat rises, the top section is at double that.
Do you have a look at the freezer, see if there's any difference?
You can't see any definition in there at all. It's very cold. Well, that's a shock revelation. The freezer is cold. Inside, it's around -18 degrees Celsius, so it's no wonder that after just seconds, Johnny's fingers have halved in temperature. Another few minutes and he'd officially have frostbite. Until 1929, fridges used toxic gases, including ammonia and sulfur dioxide as coolant. Unfortunately, several fatal accidents occurred. Today, fridges use refrigerant, a man-made chemical which absorbs heat. It's circulated by this compressor, which is the hottest part of the fridge. The refrigerant travels in the walls of the compartment, absorbing heat from the food. When it comes out at the back of the fridge, the liquid coolant is warm. As it travels down through these tubes, it cools down. The change from red to green represents a massive temperature drop. By the time it gets to the bottom, it's cool enough to pass inside the fridge again.
So that's pretty cool. A lot of people don't know that everyday objects like fridges, cheese, even people and animals are in a sense flashlights. They give off light just not the type of light that eyeballs can see. Speaking of animals, here's an elephant in the infrared, and it looks like maybe some what used to be food for the elephant. In a world where cheese and poop. I think it's cool how the ears are cold. You can tell colder parts, the tusks are cold. Armpits are freaking hot. Trunk's hot. Um, Tires are cold. It's cool. Again, these colors are arbitrary. You know, someone who made that display just made a program that said, all right, when you get really intense infrared, it's going to be red, and when you get not very intense infrared, it's going to be blue, sort of thing. So there's that. Here's one more. This is a human. Kind of cool. Might be surprised at some of the cold spots, like the upper chest. Arms are cold. Chest's cold here. Neck is super warm. Top of the back. Armpits are hot. It's kind of interesting. It's like this sort of sides of the neck are really hot. It's kind of weird. Maybe he's sick. So there's infrared. Then of course there's visible. No need to go over visible because you see it every day. You've seen it, you know, basically since you've been born. So let's go to ultraviolet. Now this is a picture of the sun in ultraviolet, but there's a lot you can learn about ultraviolet, and as you can see, this is a range, so you can have very specific wavelengths within that range. So this picture, I believe, is a conglomerate of a bunch of different ultraviolet wavelengths all mixed together. So like one color is orange, one color is yellow, one color is blue or green, whatever, and they just stuck them all together, and you can see a lot of cool things like prominences and flares and all that good stuff. But what I think is cool is this. Um, so here's a flower, photograph of a flower taken with visible light. Basically, you shine visible light on it, visible light reflects off, and you see this. And here is a picture taken, exposed with ultraviolet light. So you shine ultraviolet light on it, hits it, reflects off, although it looks like a lot of the ultraviolet light here is absorbed because it's dark. And look at the difference. Now if you're an insect, say, who likes pollen, what attracts you, or what seems to make the pollen parts of the flower, the pollen parts of the flower more obvious? Ka-ching! This one. And I remember reading somewhere that like bees can see a bit of ultraviolet, so that's cool. That's cool. You can use it for security things and money, yada yada. But here's what I think is cool. Putting on, well, first off, here's a picture. Those aren't, kind of gross. But anyway, here's a picture of um, a woman in visible light and ultraviolet, and you can see that the skin likes to absorb ultraviolet. Now, the eyes really like to absorb it too, and that's bad because the energy is absorbed and causes skin damage actually. You can tell it's absorbed because of a lack of color. If it was reflected, like maybe a lot seems to be reflected off the middle of her forehead here, maybe because of the angle facing the camera, that it would be brighter. But check this out. So this shows you essentially how sunscreen works. So she's applying sunscreen, and here is visible light, and you can see the sunscreen as she rubs it in disappears. But over here looks like war paint, and the sunscreen is doing its job. This is ultraviolet light shining, and this sunscreen is absorbing that light. So instead of the skin absorbing it, which you can tell her skin and her eyes are darker, so you can tell that her skin is absorbing the ultraviolet light. But the point of the sunblock is it's a little thin layer that ultraviolet light hits first, and so it will get absorbed in that material, whatever the sunscreen is made out of, and not the skin. So if we could see, and then she looks normal here. It rubs in nicely. You can tell something, maybe lotion on her face, but here, obvious. So you wouldn't want to have ultraviolet vision with sunblock because you look like you're maybe going to battle or something. I think that's cool. Is there any other down here? Yeah. All right. So that's ultraviolet. X-rays. So here's the sun in X-ray, and not a lot going on in certain parts of the sun, but it seems to be a lot always going on in the middle of the sun. We're gonna get to why that is, but you got some flares here. These flares are super high energy, and it makes sense because X-rays are short wavelength, high energy, given off by really hot things. Not a lot of things easily give off X-rays. But humans, we're so smart. We figured out how to not only make like an X-ray flashlight to shine on something, but we also figured out how to expose it on film. So we can shine X-rays on a person. The thing is, X-rays are so energetic that they don't bounce off the skin like visible light, or they don't get absorbed in the first layer of the skin like ultraviolet light. They go through all that, and then they reflect off denser bone and teeth, and so that's how energetic that the light is, the X-ray light. So here's a cool picture of someone eating some food, and you can see the X-rays go straight through the less dense skin and muscle, watery stuff, and bounce off the more dense stuff. Sweet. Look at that. Oh. Of course, it's kind of dangerous because X-rays, being high energy, are really damaging to cells, and so this person was very kind to subject themselves to these harmful high energy X-rays. What happens is the photons of light will, go in and hit cells and damage the DNA in the cells, and the cells are like, oh, I no longer have my instructions on how to properly, that's cool. I no longer have my instructions on how to properly replicate, so I'm just going to replicate over and over without stopping ever. And that's what cancer is, just uncontrolled cell growth. It's cool, you can see the lungs. Of course, those of you taking anatomy are probably know a lot more. Whoa, know a lot more about this than I do. Just to swallow involves so many muscles and so much. Look at that. Just in a world where swallowing. I gotta stop doing that. Sorry. Alright, there's X-rays. And finally, gamma rays. This is this is a picture of the sun in gamma rays. Not much to see. In fact, this is really just where there was a flare. The sun is not really energetic enough to give off gamma rays consistently or constantly. You need like really energetic, like sorry, supernovas or things like that. So yeah, this is a picture of our galaxy, and of course these are other galaxies and things. This middle band is the Milky Way galaxy, and you get some gamma ray sources which could be pulsars or supernovas, both within our galaxy and in other galaxies over here. So they're really bright, and it's hard to capture these X-rays. These gamma rays. They're super high energy, and so to expose any sort of picture, just yeah, it's not easy. But all right, well that's gonna. Oh, two more slides, real quick slides. So then, just to sum it up, because each wavelength of light shows different things, you can learn a lot about one particular object. Here's a galaxy. This is what the galaxy would look like to our eyeballs, with a regular telescope. But you take the same picture in radio, and you see different things. You see this feature in both the radio and invisible, but you don't see it in infrared, and then you see it here in ultraviolet, but you don't see it in X-ray. X-ray, you pretty much only see the center here, where there would be most likely a supermassive black hole. You don't see much going on in the arms. Ultraviolet, you can see star formation happening in the arms. Visible, a lot of what's going on here is obscured. And so yeah, it's pretty cool. So then you can make a composite of this. Actually, the last slide here is an even better composite. That's beautiful. Whoa. So this is our galaxy, the central region of our galaxy. So you take 3 different observatories. Of course, you all have heard of Hubble. You might have heard of Spitzer and Chandra. Spitzer takes infrared, kind of like far infrared, and this is what the center of our galaxy looks like. And you can see that in here as the kind of oranges. And then Hubble was fitted with the near infrared telescope recently, sort of ish, and you can see those as the kind of yellowy. So there's some, like this right here would be this right there, I think, yeah. And then Chandra takes pictures in the X-ray, and so the bluish stuff is X-ray, and you mix them together and you get a not only beautiful picture, but you can really tell a lot. Like something's going on here that didn't seem to be happening. Well, it's hard to say actually, because it looks like these pictures are cut off, not the same size as this. Actually, I probably shouldn't make that assumption. But there's something going on here, and you can see a little bit of something here, and maybe that's it right there. So, but you can see that like it's bigger in X-ray than it is in near infrared. So that could tell you something about this material. So pretty cool. All right, I'm gonna stop there, and the next videos will be on spectroscopy. Talk to you later.